Today, we are starting a new chapter, okay? And it's going to talk about the first section of this chapter. We talk about sequences, okay? So what is a sequence, okay? So a sequence in math right here is actually an order list of numbers, okay? So you list them one by one, okay? And the order here, there's an order for the sequence, okay? First turn, second, third turn, etc. And this one here is called the end turn, also called the general turn. So in general, the turn is going to look like this. There are many other notations for sequences. So you can actually represent it, list them over here, or you can put a pair of braces here to indicate sequence, or you can also indicate the index. The starting index here is 1, and then later on over here is 2 and 3, all the way to infinity. Okay, the sequence goes like this. Now let's look at some example. This is an example of a sequence, cosine of n pi. Okay, let's fill out the first couple terms of this sequence. What will be the first term of this sequence? Cosine of 0. Yes, you got it. So let me write down. Cosine of 0, cosine, the next one, pi, 2 pi, cosine 3 pi, etc. Right? What will be the general term, the n term? Cosine of n pi. Yes, you got it. Okay. Now, those are multiple parts, right? So cosine of that, let's try to evaluate each term. Cosine of 1, cosine of 0 is equal to what? Cosine of 0 is equal to what? 1. Yes, you got it. Cosine of pi, -1. Cosine 2 pi, 1. Cosine 3 pi, -1. And do you see a pattern? What happened? What's the pattern? Yes. It go 1, -1, 1, -1. It alternates, right? Okay. So you can write this sequence in another way. This one here. We can put the general term here as -1 to the n power. Okay. So when n is the index here, you can actually start from 0. Okay. So when n equal to 0, what's -1 to the 0 power? 1. Yeah. And then -1 to the first power will be -1. And you see the sign here alternate. So -1 to the n power actually will make the sign alternate. Okay. So remember that. Now let's try to list. Okay. Let's try to get a little bit more comfortable with sequence. Okay. By listing out the first couple terms of a sequence. Okay. This one here is the general term of a sequence. Let's find A1. So let's plug in n equal to 1. What does A1 equal to? That will be, let's just write out, right? -2 to the first power, and then over 1 plus 3 factorial. Okay. Now, for some of you, this might be the first time you see a factorial. Okay. So what is a factorial? Factorial. Okay. This exclamation sign is a sign for factorial. Okay. So it means you multiply 1 and 2 and 3 all the way to n. That's n factorial. Okay. So now the product of the first n positive integer in another case, or you can do the other way, you can go down. So you start with n and then you subtract 1 from it, it's times n minus 1 times n minus 2 all the way down to 1. Okay, then it's n factorial. For example, 4 factorial is actually 4 and then times 3 times 2 times 1, and then that should be equal to 24. Or another way to write this, you can also write this is actually 1 times 2 times 3 times 4. Okay, that's equal to 24. So you can either go down like this or go up like this. Okay, so that's what it means factorial. So 5 factorial, for example, is 5 times 4 times 3 times 2 times 1, which is 120. Okay, so that's factorial. Okay, this is one of the F words that's allowed in math class. Okay, in math we have a lot of F words. Factor, factorial, okay, function, right? Okay, all right. Now let's think about A2. Okay, what is we're not done. So in the denominator here we have 4 factorial, right? And 4 factorial is equal to what? 24, right? Okay, so let's do it over here. So that is, so you have -2 over 24 because 4 factorial is equal to 24. And reducing them, you get -1 over 12. Okay. Can you find out what does A2 equal to? All right, let's try this out, right? So it is, so up here you have -2 to the second power over 5 factorial, 2 plus 3 factorial. So you will have 4 divided by 120. Then reducing, you will get 1 over 30. Right? Okay, good job. Now the next one we want to talk about here is, now for the example before, you are given AN, and then all you have to do is substitute the index to find A1, A2, etc. Right? And now we could give you a sequence, but now you have to find the AN. Okay, you're trying to find the general formula for AN. Okay, so looking at this, can you guys find a pattern? What does the AN equal to? Very good. Let's think about, look at the sign first. Positive, negative, positive, negative, positive, and then maybe negative, okay? So you see the sign alternate, right? If the sign alternate, then you will have to put either, you're going to put either this for the alternating sign, okay? Or you can, you can either put this for the alternating side or this for the alternating side. Okay, so remember -1 to the n power or -1 to the n plus 1 power. When n go from 1 to 2 to 3 to 4, etc., you see the sign alternate. So if you see the series, the sequence here, the sign alternate, you're going to put one of these over here for the general term right here. Okay, but how do you know which one? This one or this one? Yeah, you test it out, right? So you test this out. Now this one here, n equal to 1, okay? We have positive 1/6. So if you put this one, -1 to the first power, which is -1, it's negative. So we're not going to take this one. But then if you take this one, -1 to the 1 plus 1 power is positive 1. So it matches with this one. A1 is positive. So we're going to take this one. Okay. So you test it out. Okay. So we're going to put that over here. That is for the alternating side right here. So we take care of side here. Now we can ignore the sign and just focus on the number. Right. So let's focus on the number. What do you see over here? Okay. Do you see a pattern? 1 and then to 4 and then to 9 and then to 16 and then to 25. What's in the n square? You got it, okay? Yeah, so that will be n square. Okay, good job. See, you guys very smart. Okay, so over. Let's look at the denominator. Okay, 5 and then 6, 7, 8, 9. I cannot read that deep. Okay, now n plus what? N plus 4. Yes, you got it. Okay, so that is n plus 4. Okay, n plus 4. See, this 5 is 1 plus 4, and here is 2 plus 4, 3 plus 4, etc. Okay, so you find the general term for the sequence. Okay, so that's how it is. First, take out the sign, and then you look at this. Any question over here? Okay. Next one, we get to the Fibonacci sequence. Okay, you guys remember? Do you guys heard of the Fibonacci? Have you heard about Fibonacci? You do? Okay. I think it goes this way. Actually, someone posed this question about the number of rabbits in the M1. Okay. When I look at that, I thought of my dog, but anyway, rabbit. Okay, so someone actually posed this question in the period that Fibonacci was alive, and then the person asked this question. So suppose you start with one pair of bunny rabbit, okay, and the bunny is going to become mature at the end of 2 months, and it's going to produce another pair of rabbits. So one pair of rabbit at the end of 2 months will mature, will big enough, and it's going to produce a pair of rabbits, the baby one. Okay, so this mature pair of rabbit produce one pair of baby rabbit at the end of 2 months. And then if this continue in this pattern, so at the end of every 2 months, then the rabbit that is 2 months or older is going to produce a new pair of rabbit. Then at the end month, okay, end month, for example, maybe let's say 12 months or 10 months after, how many pair of rabbits that we get? Let's look at the picture here, okay? This is the sequence. So now you start with one pair of rabbit, right? So, but it's not mature enough yet because only 1 month old. So no new pair of rabbit. Let's look at the second month here. How many pair of rabbit we get? We still have this one pair, right? Okay. Now at this third month, this pair of rabbit is still alive, okay? Assume they live forever, okay? They're still alive, okay? Still alive, so you still have this pair of rabbit. But it's going to produce a new pair of rabbit over here. So you're going to get what? This plus this, which is going to be 2 pairs, right? Okay. Now let's think about the 4 months. This pair of rabbit is still alive, right? Still here. But then it's going to produce another pair of rabbit because it's over 2 months old, right? To produce that. But then this pair of rabbit, the baby one, is going to become older and then become older. But it's not going to produce any pair of rabbit yet because it's not over 2 months old. So see here. So the number of pair of rabbit here is actually follow a pattern. Okay. So let A1 to be the number of pair of rabbit at the first month. And then A2 will be the number of pair of rabbit at the second month here. Then A3, the number of rabbit at this month is actually the sum of this A1 and A2. Okay, the sum of this A1 and A2, because this is going to produce a new pair, right? So that is going to be this is going to be this number here, A2 and A2 here equal, and then this is going to be this one, okay? And follow this pattern, you can actually get the number pair of rabbits at the end month. Suppose every pair of rabbit is going to produce a new pair of rabbit when they are 2 months or older. Okay, when they're over 2 months old, okay, and they live forever. Okay, and this is actually called the Fibonacci sequence. Now let's go to the number. Okay, so you have the first one, you have 1 pair of rabbit. Second one, you have still 1 pair of rabbit. And what will be A3? So this is A1, right? So this is A1, and this is A2. A3 here is going to be what? You sum this two, right? You sum it, and you're going to get 2 pair rabbit. Okay, so that's A3. Okay, and then the 4 month, you're going to sum. What are you going to sum? You're going to sum the number of pair rabbit in the previous 2 months, right? So you're going to sum 1 here and 2 here, and then you'll get this 3 over here. You see the pattern? And now you're going to, the next month, you're going to sum 2 and 3, and you get 5 pair rabbit. Continue like this. You see the number here, it's going to get bigger and bigger very quickly right here. Now, this is a sequence. It's called a Fibonacci sequence, okay? For this sequence over here, every number is the sum of the 2 preceding ones, okay? So like 5 plus 8, then you get 13. 8 plus 13, you get 21. And you continue this pattern. And you can only describe this recursively, okay? Recursively. Now you write down A1 equal 1, A2 equal 1, and then you put AN to be equal to the sum of the 2 terms before it, okay? So the term before AN is AN minus 1. The term before AN minus 1 is AN minus 2. So when you sum this up, you will get the AN term. So you describe this recursively. I think in computer, many of you are computer science major, right? Maybe sometimes the professor will ask you to write a program to generate a Fibonacci sequence, right? Then what kind of loop do you use to write this program? Yeah, you can define A1 equal 1, A2 equal 1, and then you have a recursive loop, right? Continue doing this. Okay, very good. So this is a sequence. Define this recursively by this. Okay. We don't have an AN general term right here. Okay, but we can describe this recursively. There's some interesting side note about this. If you're looking at the ratio of the next term over the term before it, okay, so AN plus 1 over AN, for example, like 55 over 34 or 89 over 55. Just take one term, divide by the term that's before that. What happens in the long run over here? In the long run over here, that ratio is approaching to 1 plus the square root of 5, and this quantity divided by 2. And that's called the golden ratio. Have you heard about golden ratio? Kevin say, I know that. Okay. This golden ratio here is, we call it 5. The Greek letter for that is 5. Okay, it's about 1.618, etc. So we know about irrational number pi. We know about the natural number e, and now you actually see another irrational number that's kind of interesting. It's called golden ratio. Okay, if you have a rectangle, okay, to put your map, then in art, if the length divided by the width is equal to this golden ratio, and they say that this is the most appealing rectangle to your eye. Okay, the golden ratio in art. Okay. So for example, like this one. Okay, yeah. Okay. And another interesting fact here is the Fibonacci spiral. So look at the Fibonacci spiral here. So A1 is 1. Okay, you see here. A1 is 1. A2 is 1. A3 is 2. Okay. A4 will be 1 plus 2. That will be 3, etc. Okay. Then you can actually do this. Okay. Connect this part here with this. And you can construct this called Fibonacci spiral. Okay. And for some interesting fact about Fibonacci spiral, then I think you guys, how about you guys look it up and post it in the discussion and see what you find. Fibonacci spiral. Okay, so that was the example. Fibonacci sequence is an example of a sequence that defines recursive mean. Now the next example here is this sequence. Let's write out the first couple terms. What will be the first term? 1/2? Yes, you got it. Okay. So that is 1/2. Next one, 2/3. And 3/4. Yeah, you got it. Continue this. If you graph this, what happened here? See, I have 1/2 here, right? See, I have 1/2. And I have 2/3. Continue. What do you think the AN is going to approach to? Yeah, approaching to 1, right? So A1, A2, A3, and getting closer and closer to, looks like closer and closer to 1, right? Okay. Now, to see this, you can actually this one here, you can actually use this to prove it, right? You see it, but if you want to prove it, you can actually use a theorem over here. What is this theorem over here? Okay. So it says that if the limit of the function is approaching to L, okay, what's L? Here's L. Okay. Approaching to L. Here is this L over here. So, and then we have, okay, so we have this function. Okay, so that's the function, f of x. Okay, you see f of x over here? Then what happens? It goes like this, and it's approaching to L in the long run, closer and closer to L, right? The function value closer and closer to L. Now, if you let an to be fn, okay, so what is a1? Okay, a1 here is what? Okay, let me use a different color over here. A1 here will be this. That's make it bigger. Okay, this is A1. Okay, A1 is the y coordinate of this point when the x here is 1. Okay, and A2 will be this. The y coordinate of this point when this is 2. And the A3 will be this one. The y coordinate this one when the x here is 3, etc. And then continue this way. And then you see that those are the AN will be y coordinate of those points that have the index over here to be the x value. The x value over here will be the index. Okay, 1, 2, 3, 4, etc. And you can see that those are some special point on the curve, right? You see that? So those are some special point on the curve. So the theorem says that if the function is approaching to L, okay, you see that closer and closer to this L, what happened to AN? AN approaching to what? AN will also approaching to L. You got it. Good job. Okay. Yeah, we're also approaching to L because those are the special points on the curve, right? If the curve go to L, those points here, the y coordinate also go to L. Okay, good job. Okay, you see it. Okay, So this is what the theme here says. Okay. So it had to follow the same track. Okay. So now go back to this one, this problem here. Let's find the relating function of this sequence. So we're going to replace n here by x. So we place n here by x. So you have x over x plus 1. The limit of that is actually equal to 1. You can use, how do you know? How do you know the limit of this equal to 1? You can use either L'Hopital's rule, right? Or you can use the shortcut I actually talked about in Math 110A. You look at the dominating trend. Okay, do you remember the dominating trend? Okay, when you have a polynomial, when x goes to infinity, then you look at the dominating trend, which means the trend that has the highest power on x. So here is x here and x here. Comparing to 1, the x will be much bigger because x goes to infinity. So the x here dominating over the 1. Okay, so you're looking at this. So as x goes to infinity, that is going to behave very similar to x over x. X over x is 1, so the limit of this will also be 1. Okay, like that. So that was the trick that we used in Math 110. I talk about the shortcut in Math 110A. Look at the dominating trend. Now, replacing the x here back by n, then you get the sequence. So if the function here go to 1, then this sequence will also go to 1 because that is just some special points on the curve. If the curve goes to the function value go to 1, then the sequence, which will be some special function value when the index when the x here is the natural number 1, 2, 3, 4, etc. It will also go to the same number. So it will also go to 1. Right? Any question for this part? Yeah. So you find the relating function first. You find the limit. Then that will go to the same limit over here. Okay, good. All right, now next one. Okay, this one here, do you guys remember the limit of this is equal to 0? Well, let me try some examples here first, okay? So, what will be the limit of 1 over x to the 0.2 power when x go to infinity? Okay. What happens when x go to infinity? What does x to the 0.2 power goes to? What? Yeah, it goes to infinity, right? So what happens when 1 divided by a denominator that is going to infinity? Yeah, it goes to 0. Okay, very good. So it goes to 0. Okay. So this is what it says. Okay. So when r over here is greater than, see r over here is greater than 0. See, like the 0.2 over here, right? So when this r here is greater than 0, 1 over that as x go to infinity, that's equal to 0. So this is what it says. Okay, like that. What about this one? When n go to infinity, what does n to the 1 over 16 power go to? No. Oh, you mean the final result? Okay, I just talk about the denominator. What denominator go to? Yeah, it go to infinity. And 1 over that will go to 0. Yeah, same thing, right? So when this, okay, so when this r over here is a positive number, 1 over n to the r as n goes to infinity will be equal to 0. So this is what it says. You look at this example. Okay, try to help you understand. Okay, so this, so that will give you this one here match with this one here match with this one. Okay, good. All right. Now let's try to. I'm gonna talk about the shortcut a little bit. Because it's gonna help us to the process so much faster than the divide up and down by the highest power. Okay, so let me explain that. Okay, so suppose you try to find the limit of this. Okay, now how do we do this? We look at the dominating trend. Okay, look at the trend that has highest power on n. Okay. Now, when I say dominating trend, what do you mean dominating? For example, when n goes to infinity, nq is going to dominate over n squared, right? Because think about n is say 1,000. 1,000 cube and 1,000 square. This is so much bigger than this. And then when n here may be a million cube and a million square, this is much, much bigger than this, right? So that is going to dominate over this when n goes to infinity. Same with x cubed dominates over x squared. Okay, you see this example? A million cube is much, much larger than this. And when this is bigger, the cube of this is much, much bigger than the square of this, right? So we say dominating. So you look at the exponent. I don't know you guys in computer science, do you guys talk about big O of x, big O of x squared, etc.? Who's a computer science major? Huh? Big O of n? Yeah, big O of n, big O of n squared, right? Yeah. So big O of n squared dominate is much bigger than big O of x, right? Okay, so look at the dominating trend. Basically, it's the one that has highest power on that variable when that variable goes to infinity. So looking over here, these two are the dominating trends, right? Can you tell me what will be this limit? 2 over 5. Yes, good. Okay, so that will be 2 over 5. Okay, and looking at this. And Tony did say it though. Okay, because you look at the dominating trend, 2n squared over 3n cubed reduced to 2 over 3n, right? And 2 over 3n as n goes to infinity, it goes to 0. So this is 0. So it's much, much faster if you look at the dominating trend, right? What about this one? Infinity. Yeah, okay. Yeah, because this reduced to 2n over 5, but n goes to infinity, so that's infinity. Yeah, you just need to do one more step. Remember, n goes to infinity. Okay, good job. Okay. All right. So, for someone would say, oh, you can look at the exponent. If they're equal, that will be the coefficient of this. If the down here has bigger exponent, then it goes to what? So, if up here have bigger exponent, then it goes to what? Infinity. Yeah, that will also, okay? That also works. Okay, now the next one here, we talk about a definition, okay? So, what does it mean? Today we don't have the motorcycle for this, okay? Hi. So, what does it mean the sequence has this limit L, okay? For example, what do you mean the sequence, the limit of this sequence equal to 5? What does it mean? It means that the trend of the sequence is going to approach a 5 as n become large. Okay, getting closer and closer to 5. Okay, and the sequence converge to 5. Okay, when it's equal to a number, we say that it converge. Okay, when the limit is a number, we say it converge. And what do you mean the limit over here is infinity? The limit of that is infinity basically means that then the sequence get bigger and bigger without bounds, right? So get bigger, like 1,000, over one, will be a million, a billion, etc. Right? So a million. What's the next one? Billion. Okay, etc. Okay. Okay, so it means the chains become larger and larger without bounds. Okay, as n become large. And when the limit of that is not a real number here, we say the sequence diverge. You know, converge is equal real number. If it's not a real number, it diverges. Right? Okay. All right. So diverging, converging. Here is the usual limit law for sequence, right? Remember, you can actually, it's the sum law. Okay, the limit of the sum is the sum of the limit. The difference of the limit of the difference is the difference of limit, providing that the limit for an and bn exists. Okay, and then here is the constant multiple law. If you take a constant times an, now take the limit of that. You can take the constant outside. Is the constant times the limit. Okay, and here is the constant law. The limit of a constant is the constant itself, and the limit of the product. Okay, this is the product. Is the product of the limit. Is the limit exists, and then the quotient law, etc. Right, and the last one here is the power law. Okay, so to the p power, then we'll take this to the p power, etc. Okay, when p is positive and an is positive. Next one here, we're going to talk about the squeeze theorem. Okay, do you guys remember squeeze theorem? Squeeze theorem from Math 110A? Yeah, you do? Okay, great. In Math 110A, let me draw the picture to remind you. Okay. So remember in Math 110A, we talk about the squeeze theorem for function. At that time, we have function f and h. These two functions squeeze this function g near a. So near a, g is going to be in between the blue one and the black one. Okay. Now, what happened over here is the limit of this f and the limit of h, both of them approaching to this limit over here, L. If the above and the below function approaching to L as x approaching to a, what happened here is the function that squeezed between them, the g, has to approaching to L as x approaching to a. Does it make sense? Right? So because it's going to be sandwiched, some other professors call it sandwich theorem, because the g is being sandwiched between the f and h. So if both of them approaching to L, then the one that being sandwiched by them had to go to the same limit. Okay, guys. So it's also called the sandwich theorem, which is yummier, right? And some people also call that the pinching theorem, which is more painful. And I have one student told me it's also called the Pernice theorem. Pernice. I think he's from India. So why is it called Pernice theorem? Okay, so what's like this? So this F and the H, think about like two policemen over here. And the G here is a drunk person, a drunk, okay? And the police is going to escort this drunk person into the cell. So the drunk person wiggle like left and right. But as long as the two police enter the cell, the drunk person had to enter the cell, has no place out to go. So it's also called a police thing, okay? So it had to reach the same limit out. Okay, now we have a similar thing for sequence. So what does it say? If the above sequence and the below sequence have the same limit, say L, okay, L over here, approaching to L, here, okay, then the sequence, the Bn over here, being squeezed by An and Cn, has no place out to go, have to approach to the same limit L, right? It makes sense because it's going to be sandwiched between An and Cn, so it has to go to the same limit, right? The drunk person has to enter the shop by the two police, okay? Okay, so this is what this one means, okay? And you don't have to start the index here from 0 or from 1. Okay, what really matters here is the at the end. So for example, right here, you can actually cut it off. Okay, so from some index on, let's call the N naught. After this index here, this sequence is going to be between this AN and CN. If AN and CN approaching to this limit L, then the one that is between these two has to go to the sum limit. So you just need to compare them from some index on. So before this index, this one here might not be able to be compete me between these two. Okay, it doesn't matter. We're actually more concerned about the tail. So if the tail of the sequence is going to be between these two sequence, then if the above and below sequence approaching to L, then the sequence also approaching to L. So this is what it means. Okay. So here, the N naught over here is it actually means from some index on. Okay. Okay. Now we can use this. We can actually use this squeeze theorem to prove this. Okay. What does this say? If the limit of the absolute value of AN equal to 0, then the limit of AN goes to 0. Okay. What does it mean? What's the difference between this one and this one? This one here has this absolute value. This one here doesn't, right? 0 and 0. Can you guys think about how to prove it? Any idea? Can we? Yeah.
The AN is the positive, then we don't need to use, right?
But
and the AN is negative, so it means the AN is upper the absolute value of the AN, and then below the 0, that's y equals 0.
Okay.
And then you use the squeeze theorem to prove it.
Yes, we use the squeeze theorem. Okay. So in order to use squeeze theorem, we need to squeeze this sequence, right? Squeeze this AN. AN is the sequence we try to find limit. We're going to squeeze it by one above, one below. So you got the idea. So we know that this is less than equal to the absolute value of AN. So we can use this as the above sequence. Okay, so this is above sequence. Okay, and now let's think about what's the below sequence. Okay, so greater than equal to the opposite of the absolute value of AN, right? So that is going to be between this one and this one. Okay, so we can squeeze this between these two sequences. Now, what do we know about the limit of this? This sequence goes to what? It goes to 0. And what about this one? What does it go to as n goes to infinity? Yeah, that also go to 0, right? Because it's going to be negative of the limit of this. The limit of that is 0. So negative of 0 is 2 0. So it's 0. So the above and below sequence both approaching to 0. What can we say about this sequence? It has to go to 0. Yes, you got it. Squeeze it, right? Okay. So that's the idea of the proof. Okay. All right. Which page am I? Oh, we are on page 3. Okay. Let's try to use this. Okay, this one here. Find the limit of this. Well, you guys know how to do this, right? You guys want to use. Okay, over here. Let's go through the book way. Okay, what did the book do? The book over here did here to find this limit. You divide up and down by the highest power in the denominator, which is this n. So divide by n up and down. You get 1 over, divide n by n, you get 1, divide by n, here you get 1 plus 1 over n. As n goes to infinity, 1 over n goes to 0. So you get 1 over 1 plus 0, so it's 1, right? So the limit is 1. But how about we use our shortcut to do it? Can we use our shortcut to do it? Okay. What's our shortcut? We look at the what? Yeah, look at the dominating chain, n over n, right? So the limit of this will be equal to what? N over n, which is 1. Okay. So that's why I want to explain and mention about a shortcut so that it saves you some time to see what's going to happen quicker. Okay. So that's it. All right. Oh yeah. You look at the dominating chain. Okay. Dominant chain. So that is going to be 1. Okay. Look at this one over here. Look at this one here. If I use a shortcut, what would this be? It's infinity? You got it. Okay. So look at this power. It's n to the first power. This is n to the 1/2 power, right? This is higher, so infinity. You got it. Okay. All right. So it goes to infinity. Okay, good. Now, if you don't use a shortcut, then you can do it this way. What did you do? Over here, they divide by n up and down. Okay, divide by n up and down. You simplify it like this. And you find the limit here, also infinity. Okay, so you can either use a shortcut or you use this way. Maybe this one make more sense to you, but either way, okay? Okay, so we practice on this. Okay, we got this part here we did already. Yeah. How about we take a break? Take a break? Okay, come back. In 10 minutes. Right, let's continue to get this done, okay? In this example, we're trying to find this limit over here. I cannot use a shortcut right here because this is not a polynomial of a polynomial, right? You cannot do that. But kind of similar to the shortcut though. Okay. Now, but someone would say, how about I replace this n here by x, right? So you have ln of x over x. That is what type of this limit? It's infinity over infinity. Yeah, then you use the L'Hopital's rule, right? Apply L'Hopital's rule, rush the hospital. So you can apply L'Hopital's rule. What's the derivative of ln of x? 1 over x. And the derivative x is 1. Then the limit here is going to be 0. Now, when someone say, can you just go ahead and apply L'Hopital's rule for that one? Tony, no. You cannot apply L'Hopital's rule where it's n. You cannot do it over here. Why? Because over here, what's n? N is what? The index, right? It's 1, 2, 3, 4. It jumps. Okay? So it is ln of n is not a continual function of a real variable. It has to be a continual function of a real variable. Because when you differentiate, it has to be a differentiable function. Differentiable function has to be continuous first. So if it's not continuous, you cannot differentiate. Okay? So then what you have to do here to make things simple, you just need to remember, you just need to replace the n here by x. Then you apply L'Hopital's rule. Like that. Okay? And then you're safe. Because now it's a function of real variable. Then you can apply L'Hopital's rule. But if the limit of this is equal to 0, then what happens to this limit here? Inside the x, you have n. What will be the limit? Will also equal to 0 because this one here, according to the thing we just talked about, right? If the function goes to the limit, then the sequence also go to the sublimit because those are the special value in the function, right? Okay. So they follow the same chart. Okay, remember this one, right? Remember last time we talked about the function, right? So the function go like this, and then approaching to L, and then the sequence is going to be, so special will be the function value at those special points, right? So if the function go to L, then the sequence also go to L. Okay? So this kind of problem, you just replace the n here by x, and then you apply L'Hopital for that. And then if you get a number here, then the sequence will also apply approaching to this number. Okay? Okay, so that's the idea. And here's the explanation why you cannot apply L'Hopital directly when it is n. Okay, so some explanation. Okay, the next example. This is the alternating sequence. -1, 1, -1, 1. Do you think this sequence here converge? How say no? Why? Why not? It diverges because sometimes it go to 1, right? Sometimes it go to -1. So actually, it's going to alternate, right? Some 1, -1, 1, -1, 1, -1. Keep on going up and down, 1, -1, 1, -1, right? It doesn't go to a fixed finite number. So we say that this sequence here diverge. And in picture, you see like this, right? So this. So this one here is divergent. The sequence diverges. Okay? And you see that the even turns goes to 1, and the odd turns over here go to -1. So it doesn't go to a fixed number, right? So it diverges. So when it doesn't go to a fixed number, then we say the sequence diverge. Now here is the theme over here. Okay? What happened over here? It says that if the limit of an here is equal to L, okay, let me highlight this one. So this an over here, as n goes to infinity, it actually approaching to L. Okay, now this one over here is L. Then if you have a continuous function adding on the sequence, the limit of this function of this sequence is the function of the limit. In other words, if the function here is continuous, you can actually bring the limit in. Okay. So in 110a, we actually talk about if the outer function is continuous, we actually can bring the limit in. Okay. So you bring the limit in here. How do you use this thing? Okay, let's use some example to understand this thing here. Right. So before that, I think I skipped this part here. Okay, let's try this one. Example 8 first. Okay. For example 8, we try to evaluate this if this one exists. So how do we do this? Well, if this one here has the alternating side, right? The -1 to the n power, it's the alternating side. Okay. However, we're taking, so when we take the limit of this, we actually can put the absolute value on that sequence, because that way I can ignore the alternating side. It all become positive, right? So I will have this 1 over n. So can ignore the alternating side. The limit of 1 over n is 0. Therefore, this limit here will also equal to 0. Why? Why is that? Did I just say over here? The same over here, right? The limit of the absolute value of the sequence, if it's equal to 0, then the limit of the sequence will be equal to 0. Okay. Try to visualize it in the picture. Okay. So if you put the absolute value over here, then it is 1 over n. Okay. In the picture here, you can think about it as the distance from the point to this axis. Okay. It's 1 over n. And as n goes to infinity, it's going to approach to 0. Okay. So you have this, and you have this, this. But it gets closer and closer to the axis. You see that it's getting closer and closer. Okay. So if the absolute value of that is approaching the 0, then this sequence itself will also go to 0. Okay. So we can. So sometimes if you see the sequence, the sign is not always positive. You can actually take the absolute value of that, okay, and see if the sequence go to 0 or not. If it go to 0, then this original sequence will also go to 0, okay, because of this thing. Okay, so sorry, this is out of order. Okay, but that's the example using that thing. Now go back to this one. This one says that if this function, this outer function here is continuous function, you can bring the limit in. Okay, bring the limit in. So limit of the function is function of the limit. Okay. Okay, now how do we use it? So look at this example. We have sine of pi over n. Look at the outer function. The outer function is a sine function. I said if it's a continuous function, why? Does it have any break for sine function? Right? Sine function doesn't have break. Continuous. Okay? So when it's continuous, you can actually bring the limit in. So that will be equal to sine of what? What should I put over here? Yes. Right. You can bring this limit in. So limit as n goes to infinity of this pi over n. Okay. So bring this limit over here in. So limit of this function is function of this limit. Okay. Now we find what's this limit? Pi over n as n goes to infinity. It's going to be 0. Okay. Because the denominator go to infinity, the numerator stay fixed as pi. Divide the bigger number here, it goes to 0. Okay, so it is 0. What's sine of 0? Yeah, you get 0. Good job. Okay, so you got that. So when this outer function is continuous, you can actually bring the limit in here. Okay, the next example. This next example, we try to see the convergence or divergence of this sequence. Okay, let me write this out a little bit bigger. Now, when you first look at this, I say, what is that, right? Sometimes if you kind of try to get an idea of how it behaves, it's better that you write out the first couple terms, okay? So my suggestion here will be try to list the first couple terms to get an idea how the sequence looks like, okay? Let's try A1. A1 over here is, okay, I'm going to list out this way. A1 is what? It's going to be 1 factorial over 1 to the 1. What's 1 factorial? 1. 1 to the 1, 1. So that is 1, right? Let's write A2. A2 is what? 2 factorial over 2 to the second. What's 2 factorial? 2. So you get 1/2, right? Okay. Okay, let's try A3 for each half. 3 factorial, right? Yeah, over 3 to the 3 power. Or maybe write in the long way. 3 factorial is 1 times 2 times 3 over 3 times 3 times 3, right? Okay, let's write A4. 4 factorial over 4 to the 4. 1 times 2 times 3 times 4 over 4 times 4 times 4 times 4. Do you see a pattern? Do you think it gets bigger or smaller? Yeah, someone says smaller. How do you know? Yeah, because you see, the biggest number here you get is 4, right? And then here will be small. This 3 is smaller than 4, 2 is smaller than 4, 1 smaller than 4, right? And here the biggest number here is 3/3, 2 smaller than this, smaller than this. Okay. So actually, so how would you like to? Okay, so you can see that the pattern here you think is getting smaller and smaller. Okay. Now I have this note over here. Okay. Now if it is getting smaller and smaller, and what do you think it's going to go to? What do you think? Yeah, you think it's going to 0, right? Okay, that's going to 0. So how do we prove it? Okay, how do we prove it? Maybe we can use squeeze in. Yeah, you're right. We can use squeeze in. So we can try to squeeze it by 1 above, 1 below, right? So how about we squeeze it below by 0? Because I know that this is positive, right? So never going to be below 0. So the below one, I can put down 0. Okay, how about the above? If you put 1, you can use it squeeze in. Can you think about one that squeezes? Okay, let's take a look at here. Let's take a look here, right? N factorial is 1 times 2 times 3 all the way to n. N to the n here will be n times itself n times. Now, I'm going to actually leave this one alone, 1 over n alone, leave it, set it aside, and just group the remaining part over here together. And I claim that this part here is less than or equal to 1. Can you tell me why? Why this is less than or equal to 1? Yeah, because all of this factor here is less than or equal to n, right? So the denominator is always bigger than or equal to this. So this is less than or equal to 1, right? Agree? Okay. So that means this one here is less than or equal to 1 over n. You agree? Yeah, 1 over n times something less than or equal to 1 is less than or equal to 1 over n. So we can actually use this as the above sequence, 1 over n, right here, right? This is less than or equal to 1 over n, okay? Now I'm going to ask you, as n goes to infinity, what does 1 over n goes to?
0.
Go to 0, and 0 always going to 0, right? It's a constant sequence. So being squeezed by this too, if both of them go to 0, what does an goes to? It has to go to 0, no place else to go, right? Okay, as someone will say, how do you know to do this above sequence as 1 over n? You try to group them. You try to experiment with this, okay? So you see, because I kind of see that this part here is less than equal to 1, and try to compare with that. I think this part here might be the hardest part to see which, what will be the sequence above, okay? And also go to 0. So try to sometimes group some of the vector together and we see it, okay? All right, so then you prove it, okay? Use a squeeze here. Okay, so that will go to 0. Okay. Now, as I suggest, you will write down the first couple chain, you see the pattern. You get 1, 1/2, and here you get something smaller, and go to 0. And you can see that kind of go to 0. So you try to think about a sequence that's above also go to 0 by maybe grouping some part here together and compare with that one. Okay. Okay, so that was the squeeze theme, using the squeeze theme. Okay, the next one over here is a theme that we're going to use it in the future. So how about we go for this one now? Okay. Well, to start with this, maybe I try some examples first. What is the limit of 1.1 to the n power when n goes to infinity? If you keep on multiply 1.1, use your calculator, right? Times 1.1 times 1.1. Okay. So think about, think about positive in your life, okay? So every time you improve a little bit every day, right? You're more than one of yourself, okay? So 1.1, so I get 10% better, okay? And then next time you multiply by 1.1, right? Better and better and better, okay? So, and then as the day go on and n goes to infinity, what does this goes to? Infinity, yes, you can get to infinity, okay? You actually get to infinity, right? 1 times 1. So when the base here is bigger than 1, and you keep on multiply by it, it gets bigger and bigger and bigger and bigger. Actually go to infinity, okay? Like that. So every day it just need to improve a little bit. Okay, it can get very big, very good, okay? Now, what about limit of 1 to the n? 1 to the any power is what? 1 to the n is what? It's just equal to 1, right? Okay. 1 to the any power will be equal to 1 itself. So it doesn't matter when n goes to infinity, right? So the limit of this will be what? This 1. Yeah, it stays as 1. Okay. All right. What about 0.5 to the n power? Like 1/2. Yeah, someone would say 0. Okay, you're right. It's 0. Okay, it's like then every day you only do half the work. like worse than before, right? And then pretty soon it's approaching to 0. Okay, okay. So it's going to be this. Okay. All right. So it goes to 0. Like 1/2 times 1/2 is a quarter. A quarter times a half, 1/8. Okay. 1/8 times that is 1/16. So it's going to 0 really quick, right? As the n goes to infinity. Okay. What about this? Negative 0.5 to the n power. It's also going to 0. Okay. All right. What about negative 1.1 to the n power? I said it diverges because when n is odd, that will be negative number, right? When n is even, it will be positive number, right? It diverges, okay? All right. So actually, we have a theme over here. We in the past I actually proved this, but right now I'm not going to prove it. So what does it say? This theme here says that the sequence, okay, if looking at this R, okay, what is this R over here? R, okay. If R over here is between negative 1 and 1, for example, okay, is like 0.5, that's between negative 1 and 1, negative 0.5, that's between negative 1 and 1, then the limit of that is equal to what? It's equal to 0. The limit of that equal to 0 right here. Okay. So it converges equal to 0. When the base here is between negative 1 and 1, like this, n goes to infinity, it goes to 0. And then what happens when r equal to 1? When r equal to 1 is which case? When r equal to 1 is this one. Okay. When r here is equal to 1, is this one. Then the limit of that will be 1. Because 1 to the any power is still 1. Okay. It's also convergent, right? It convergent to 1. Okay, convergent to 1. And what happened is outside. What happened is greater than 1. If it's greater than 1, it's going to be what? Like 1.1. Then it go to infinity, right? If it's negative 1.1, it diverges. So it's going to diverge here and also here. So if it's bigger than 1 or smaller than negative 1, okay, it diverges. Okay. It's actually when it's negative 1 here, it also diverges. Okay. So this is one of the theorem. So actually, well, I have a picture over here. Okay, I have a picture here. So when R is actually between, you see here, R between 0 and 1, like 0.5, the limit of R to the n go to 0. Okay, you see here, the pink one goes to 0. And when R is equal to 1, 1 to the n power is to 1, so it stays as 1. When R is greater than 1, if you say 1.1 times 1.1, and we'll keep on getting bigger and bigger to go to infinity. And you see over here, when R is between negative 1 and 1, it go like sometimes positive, sometimes negative, but you can see that it's getting closer and closer to 0. Okay, like negative 0.5. Okay, it get close, negative 0.5 to the n power, it get closer and closer to 0 right here. Okay, even though the sign alternates, but it's kind of like a slate, go up and down, but it's getting closer and closer to 0. Okay, when R is less than negative 1, say R is equal to negative 2 to the n power actually diverges because sometimes positive, sometimes negative, but it gets further and further away from the 0. Okay, it gets further and further. Okay, so that will be a picture to see. Okay, definition. Right? What do you mean sequence is increasing, right? You can see in the picture, the sequence increasing is going to be going up, right? The number gets bigger and bigger as the index go on. And decreasing means the trend gets smaller and smaller as the index increase. Okay, so that's decreasing. What do you mean monotonic? Monotonic is actually either increasing or decreasing. Okay, so if it's increasing, it's monotonic. Decreasing is also monotonic. Okay, monotonic in Chinese we call it 单调. Means a single tone. Okay, so monotonic, so it's either increasing or decreasing. Looking at this sequence over here, we say that it is decreasing. Why is it decreasing? Well, it's decreasing. You can prove it. Okay, how do you prove that it's decreasing? To prove it's decreasing, we need to prove what? AN is going to be, AN is going to be greater than AN of plus 1, AN plus 1, right? So the trend is going to be greater than the trend next to it. Or in other words, the next trend is going to be smaller than the trend before it. That's called decreasing, right? So we're trying to prove this, right? So how can I prove this? Then you just go ahead and substitute, try to compare AN and AN plus 1. AN is 3 over n plus 5. And AN plus 1 is what? 3 over n plus 6. So if you can somehow prove this one greater than this, then we prove that the sequence is decreasing, right? But is it clear why this one here is greater than this? Why? Can someone tell me? Yeah, they have the same numerator, but then the denominator is bigger than that, right? So that's smaller. So that check. Okay. So same numerator, the larger the denominator, the smaller the quotient, right? So this one here is clear. Okay? So we prove that this is actually decreasing. Okay, the last example here, we try to show that the sequence is decreasing, right? So in other words, we're trying to prove that an plus 1 is less than an. If we try to prove that it's decreasing, right? So you just go ahead and put it over here. Okay, so you substitute n plus 1 and substitute n, and you can try to prove this. If I can prove this, then that means this, and the sequence is decreasing, right? Okay. Now, the different way to do this, one way to do that is do the algebra, okay? Can we multiply both sides by the LCD? Yeah, we can multiply both sides by the LCD, right? By this and this, okay? Which is the same as cross multiply, okay? So multiply over here, what do you get? So let me do the work. So you have n plus 1 times n squared plus 1, okay? And we try to prove this is less than n times n plus 1 squared plus 1, right? If you can prove it, right? Alright, but how can I prove this? Any idea? Yeah, you multiply out, right? So you multiply that, distribute, okay? So distribute over here, you can get, okay, here, okay, what do you get here? That you get n cubed plus n plus n squared plus 1, right? Less than n times, okay. Now we haven't done a lot of, so this is a good time to do some algebra. So this one here, we use a perfect square, right? So what would this be? N squared plus 2n plus 1, plus 1 plus 1, so that will be plus 2, right? Okay. Do we distribute over here? Yeah, distribute, okay. So you get what? N cubed plus 2n squared plus 2n. On this side, you get n cubed plus n squared plus 1. Okay, so can we substitute, subtract both sides by n cubed, right? Subtracting is not going to change the inequality sign, okay? What else can we subtract on both sides? Yeah, we can subtract n squared, right? So subtract n squared on both sides. So you will have this one here will just get n squared, okay? And we'll also subtract both sides by n. So that will be just n. So finally, this reduces to proving 1 less than n squared plus n, right? Agree? If we can prove this, then we can go backward and get this result, right? But how do you know this is greater than 1? Okay, we can actually factor this, right? Can we factor this? It's the same as n times n plus 1, right? How do we know this is greater than 1? What do you know about n? N is 1, 2, 3, 4, etc., right? So what's the smallest n you can get? 1. So you have 1 here times 1 plus 1 will be what? 2. But then as the n get bigger, this one here will be bigger than 2, right? So is this true for all n? Yeah, it's true for all n. So this is true for all n, because n is 1, 2, 3, etc. So if this is true, we can go backward. Then this is true, this is true, this is true, this is true, and therefore this is true. And then we just prove that the sequence is decreasing. So a lot of times to prove things, we go backward. So if I want this, I need this, I need this, I need this. If I have this, I can go back. Okay. So the idea of proof is like this, the thinking. Okay. Okay. Another one here to prove it. I have another student. Actually, my 110C say, he said that he didn't learn I say he want to learn more about pool. So here is some just idea, some taste of pool by induction in the next one. Actually, pool by induction. Well, later on. Okay. So here's just a simple idea of a simple taste of pool. Okay. Also, I just want to point out to you, we learned about polar coordinates, right? This is actually from my last 110 class, so you can see in the polar coordinates. So make sure you guys, if you want to go on to 110C, it's actually good to remember the polar coordinate. Okay. Okay. The next one over here. How do I prove this? How do I prove this is a decreasing sequence? I can actually prove the relating function is decreasing, right? So I have an is n over n squared plus 1. If I replace the n here by x, see the n over here replaced by x, then you have this function. If I show that this function is decreasing, then I'll be able to show that this sequence is also decreasing because this is just a special point, right? Remember the function value? This is just some special function value over here, taking the x here to be 1, 2, 3, 4, etc. Right? So how can I prove this function here is decreasing? You guys remember 110? How do you prove a function is decreasing? I saw you guys rolling the eye. To prove a function decreasing, you show the duality is negative, right? You guys remember the increasing decreasing test? If the duality is positive, then the function is what? Increasing. If the duality is negative, then the function is decreasing, right? Okay. So if we can show that the duality is negative, then the function is decreasing, then the relating sequence here will be decreasing. So over here, we actually use the duality. Take the duality. What kind of rule do you use to take the duality? Quotient rule, right? So use the quotient rule, we take the duality, and I say that this is negative whenever x squared is greater than 1. Why? What do we know about, yeah, you got it. What about the denominator? What do you know the denominator? It is a square, right? Would that be negative? No, it's always positive. So this part over here is always positive, right? So the sign of the duality depends only on this 1 minus x squared, right? So if that is negative, then the whole thing negative. So when would this be negative? Yeah, when x squared is greater than 1. Okay. So we know that. Well, what happened to n? N is go from what? 1, 2, 3, etc. Right? So that means you're only taking what happened to the x squared when x is 1, 2, 3, etc. Would that be greater than 1? Well, except the first one, right? Except the first one. Okay? So it's going to be greater than 1 when the index is from 2 on. 2, 3, etc. The square of that will be greater than 1, right? So remember last time we talked about it really doesn't matter for the head of the sequence. What's more important is the tail of the sequence. Actually, the function is actually it's 1. Let me actually draw it. Greater than 1. X squared greater than 1. Over here. So when x is actually from 1 to infinity, then the function is decreasing. Okay, so over here you have 1, but then after 1, the function is going to be decreasing like that, right? Okay, so the index over here is 1, and then 2, and 3, and 4, etc. So the function value will be decreasing. It follow the same pattern, right? Same track. Okay. So we prove that this function here is decreasing on 1 to infinity because when x is greater than 1. So then the function is decreasing on 1 to infinity, then the relating sequence is going to be decreasing because the index is 1, 2, 3, 4, etc. Okay, so that's another way. Do you guys like this way or the first one, the algebra? You like the first one? You don't have to do the calculus. Okay, all right, okay, all right. Thank you for being so honest. Okay, the next definition, we're almost done. Okay, the next definition here is a bounded above, bounded below. Okay, so what does it mean bounded above the sequence? That means it has, try to think about this picture. See, the pink one here is has a value. The y value will be m. So you see the sequence over here never go beyond the, it's kind of like the ceiling. So this sequence is actually bounded above. Okay, what does it mean bounded below? It's kind of like the floor, and the sequence never go below this floor. Then it's bounded below. Okay, so that's bounded above and bounded below. So a bounded sequence will be bounded above and below. It has a ceiling and also a floor. Okay. Then this one here is called a monotonic sequence. Okay, what does it say? It says every bounded monotonic sequence is convergent. Do you guys remember what's monotonic? Monotonic means either increasing or decreasing. Okay, let's consider the two cases. So if the sequence is bounded above and the sequence is increasing, okay, think about this picture, then the sequence has to converge. Why? Because if it's bounded above and the sequence is increasing, according to this thing, we haven't proved it, okay? It's actually it's going to be a long proof. But the theme says that if it's bounded above and the sequence is increasing, it has to converge. Actually converge to the least upper bound. Okay. So what about the sequence is bounded below? Well, if the sequence is bounded below and the sequence is decreasing, then it's going to converge. Okay. It's going to converge. Okay. So this is what it means. Okay. Now we're almost done. Okay. I always give you hope. Next one, I'll give you a taste of mathematical induction. Okay. How do you prove that by induction? Okay. So it will say something like this. It will say, the statement is true for the number, say for n equal to 1. Okay. And assume that, okay, if I can prove that if the statement is true for n, then it's true for n plus 1. So if it's true for n, then it will also true for n plus 1. Then the whole thing will be true for all n equal to 1, 2, 3, 4. Okay, it's kind of like this. Okay, so when n equal to 1, if it's true, okay, and number 1, you prove this. Number 2, it says that if true for n, then true for n plus 1. Then from this 2, you're able to say that it's going to be true for all n. Why? Well, if you can prove that it's true for 1, so this is true, right? So you prove that this is true. But then you did prove that if it's true for n, then the next one is true. So because it's true for 1, so would that be true for 2 also? Would that be true for this also? Yes, it's true. Because why? Because if it's true for n, that's true for n plus 1, right? So I proved the first, okay. So first one, I proved that n plus n equal to 1 is true. So that was true. So I put a check mark over here. Okay, that's true. Then the next one say, if it's true for n, then it's true for the next one. So here, if it's true for 1, then it's true for the next one. So true for 2. So I prove that this is also true. But if this is true, would that be true for the next one? Yeah, because of that. So it's true. And then we keep on going, right? It's true for the next one, true for the next one. Then it will be all true. Okay? Okay, it's kind of like this, right? You guys all line up, right? And say, okay, I'm true. And then the next one is true, the next one is true. And then you pass on, right? Keep on going until it just keep on going like this. So it's true for all n. Okay? So this is called induction. Okay, let's have a taste of this. Okay. So we have this sequence defined by this recurrent relation. A1 equals this, an plus 1 equals this. Okay, let's write out the first couple terms. This is A1, A2, A3, etc. Do you see a pattern? What do you think an is going to oppose to?
6.
Yeah, you said 6? Yeah, it is right. Looks like getting closer and closer to 6, right? But how can I prove this? Okay. How can I prove it? So remember the monotonic sequencing. If a function is actually increasing, right? Function. If the sequence is increasing and it is bounded above, then it has to go to a finite number. Yeah, right? Okay. So I can show that this sequence here is increasing. Okay, and I can also show that it's bounded above. Then I can find the limit like this. Okay. How do we show that this is an increasing sequence? How do we show ak plus 1 greater than ak? Use induction. Okay, use induction. So first of all, is it true for n plus 1? In other words, is A2 greater than A1? Is it true? Let's look at A2 and A1. What's A1 is this, right? A2 is what? 4. Is A2 greater than A1? Yeah, that's true. So this is true for n plus 1, right? So that's true for n plus 1. Okay, the next thing here is you will do this. Assume, okay, so this is the first one, and then the second, you're going to assume that it is true for n equal to k. Then we try to prove that, we try to show that, try to prove this true for n equal to k plus 1. Okay, so this is the first step. Okay, so this is the first one. The second one, here we say if true for k, then true for k plus 1. Okay, so you prove this. Prove this. Okay. So how can I prove that this? So if it's true for k, then you will have ak plus 1 is greater than ak, right? This is what it means, right? Is it what you mean? True for k, so you will have this. But what does it mean is true for k plus 1? What does it mean? That means a of k plus what? 2 has to be greater than a of what? K plus 1. So you're trying to prove So if I have this, I will try to have this. So you try to relate this one with this one to build from here to here. Okay, how do I do this? Okay, AK plus 2. Okay, how is that related to AK plus 1? What does it say here? According to this formula, AK plus 2 is what? Yeah, you got it. So it is 1/2 of AK plus 1 plus 6, right? It's actually this one. Okay, I don't need to write it down. It's right here. So it's this one, right? It's this one. So you can try to prove this one greater than this, okay? But here, you can relate to AK plus 1, okay? This one here is related to AK plus 1 by this way. That is AK plus 1 plus 6 first. So you're going to add 6 to both sides of this equation. And then later, if you add 6 to both sides of this equation, will the inequality sign here change? No change. And then now you divide both sides by 2. Would the inequality sign here change? No. So from here, you're able to prove this is greater than this, which means this is true. So you just prove that if it's true for k, then it's true for k plus 1, which is this one. Now, by math induction, we have actually proved that this is true for all k. Okay, k to be 1, 2, 3, 4, etc. So this is actually an increasing sequence, okay, proved by induction. Okay, if it's an increasing sequence, then if we can show that it's actually bounded above, then it's going to converge, right? So how can I prove that it's bounded above? Bounded above, let's say bounded above by 6. How can I prove that? You see that all of them not over 6. Can we use induction again? Right? So if you use induction again, so we show that number 1, is A1 less than 6? Yes, it's true. Okay, number 2. Number 2 is true for K, then true for K plus 1, right? So now if it's true for K, then you will have AK is less than 6. How can I prove that this is true for K plus 1? Which means AK plus 1 is less than 6. Let's write this up. What's AK plus 1? 1/2 AK plus 6, right? Like that. If I can show that this is less than 6, that's okay, right? Now, I have this one over here. So all I have to do is I'm going to add 6 to both sides of the equation, right? If you add 6 to both sides, this is going to be true, right? Now to build toward this end, what do I need to do? The next step. Yeah, you add 6 here, and then what do? You multiply by 1/2 on both sides, right? Then you will end up with this side will be AK plus 1, and that will be also less than 6. So I just proved that this is true for K, then it's true for K plus 1. By math induction, this is true for all K, right? True for all K, because true for 1, then will true for 2, true for 3, etc. And just induct, okay? So I show that this is going to be less than 6. Then I see that the limit here is going to, there's a limit for the sequence because it's increasing and it is bounded above. So it's going to approaching to a limit L. How can we find the limit L here? Let's try it out, okay? So what we have here, A of n plus 1 equal to 1 over 2 times A n plus 6, right? We know the limit here exists. It's going to go to L. I'm going to ask you, as n go to infinity, what does an go to? Goes to L. And what does this one goes to? Also go to L. Yeah, very good. Okay. So if I take the limit as n go to infinity on both sides, I would have L is equal to 1/2 L plus 6. Now we get a simple equation. If you solve this simple equation, what does L equal to? L is equal to 6. Yeah. So you see that the limit over here is going to be 6 like this. Okay? All right. You did a lot of serious stuff today. Okay, good job. Okay, thank you.